Okay. Hello, everyone. Let's get started. Sorry for being late. There's some issue with this microphone setting. Okay. So yeah, I want to announce that next week there will be no classes because I have to travel to National Science Foundation in Washington. Unfortunately, the flight was scheduled right between Tuesday and Thursday, such that I cannot like come to the class and present. But anyway, we'll have the office hours remaining. So please leverage this time to work with your homework 3. And we'll also cancel the quiz for next week. And yeah, but we'll have the office hours there. Okay, any question? Oh, great. And anyway, we'll make an announcement in Canvas and to make sure like everybody receive the message. So next Tuesday, don't be surprised. You come to the classroom, there's no one there or it's just empty. Okay, so let us continue with probability density function and cumulative distribution function, right? So so far, what we're talking about are for the continuous random variables, right? So we have emphasized a lot that the continuous random variable are different from discrete random variable. And so is their definition of the probability density function, right? So for the discrete random variable, the probability density functions is also called probability mass function. Basically, it means that the function value, say fa, for discrete random variable is just the probability that the value of the x equals to a, right? So this is for discrete random variable, which is really non-zero. However, for the continuous random variables, because the sample space is really infinite, continuous, right? So this probability, the probability for this event, x equals to some specific value a, is simply 0. So the probability density function doesn't have a straightforward meaning for some time, for some type of events, right? Instead, the probability density function is defined in an indirect way. So basically, if we can find a function who is non-negative, the integration with this function from the whole real world space, real number space is 1. And also, the calculation of the probability, the calculation of this probability between any of the event in any range a and b can be written as the integration of this function in a and b. Then we say this function is a PDF. Okay, it's a mathematical definition. It's not like intuitively connected to any specific type events. Right? But with this definition, we can very naturally lead to the definition of the cumulative density function, right? So the cumulative density function, sorry, it's not cumulative density, it's cumulative distribution function, is defined as the probability of a particular type of events, right? This event is described as the random variable less than or equal to some specific value a. Right? So at this point, the definition of the CDF is exactly the same as for the discrete random variable. They have the same meaning. It's just meaning, okay, the value of the CDF at any value a, right, and input a, is just the probability of the event defined as x less than or equal to a. Okay, and then associated with associating this definition with the PDF, the CDF is defined as the integration of the PDF through minus infinity to a, right? This is actually directly builds the relationship between the CDF and the PDF. On one direction, we say when we integrate the PDF probability density function from minus infinity to any value A, to any location A, it gives the value of the CDF at A. On the other hand, which is also very, very important, is if you take the derivative of the CDF with respect to A, you recover the PDF, right? So this relationship just comes from the definition of the integration function or antiderivative function. Okay, any questions so far? Oh, I hope everyone is comfortable with this definition. Okay, so then we start our first example of the continuous random variable, which we call uniform distribution, right? So I'm gonna erase all of this because it looks messy, right? So, so the uniform distribution are usually used to describe the random phenomenon such that every outcome has the equal chance to be observed. Like for example, if you want to throw a ball on this table, right? And if I believe the chance the ball hits every location on this table surface is the same, then I should use uniform distribution. Right? So the probability density function, PDF, is defined in this way. So you need to first specify the range of your random variable. Usually, you can assume, okay, it is between alpha and beta. And alpha beta can be arbitrary numbers, but you just make sure alpha less than beta, right? Alpha or less than or equal to beta, right? And then the PDF is defined as a piecewise function, right? Inside this range, the PDF is a constant, which is 1 over beta minus alpha. Right? Beta minus alpha is just the length of the interval, right? However, when x is not taking any values inside this interval, say it is less than alpha or bigger than beta, then the density function PDF is simply 0. Right? This is the definition of the probability density function for uniform distribution. So if we want to have a nice looking, right, it should be something like this, right? So that is what a PDF for uniform distribution look like. And then we use this PDF to calculate the CDF for uniform distribution. So this calculation is a typical practice of calculus 1, right? And if you feel kind of blurred about how to do this, you just need to practice again. So basically, as we mentioned, right, the CDF is defined as the integration of the PDF from minus infinity to the A, right? So what you need to do is just calculate this integration according to different A, right? And then we consider 3 cases. When A is sitting here, meaning that A is less than alpha, right? In this case, remember you're integrating through minus infinity all the way up to A, right? When A is less than alpha, we know the PDF is always 0. So that means this integration is always 0, right? And when A is in between alpha and beta, so here, right? Then your integration will, again, I mean, from minus infinity all the way to a. Sorry, I don't know why it's equals so large. Let me put it even lower. Mhm. And then you see that when you integration before alpha, all those um, PDF function value is 0, right? The PDF is only non-zero when you start from alpha, right? So the integration, effective integration will start from alpha to a. And then your fx now inside the integral will be this guy, right? 1 minus beta, 1 over beta minus alpha and dx. Then you do the integration, you say it has this linear form. Right? It's a minus alpha over beta minus alpha. Right? You don't need to calculate right now, but just we just want to quickly review what we have discussed on Tuesday. And in third case, when your a is moving even on the right, say it is on the right of beta. So the integration again, I mean, the integration is still from minus infinity to a, right? You know that, okay, when you integration from minus infinity to alpha, those are 0, right? And then your integration from alpha to beta, now the PDF is non-zero. This integration is simply 1. I mean, you can verify this after class, right? And then start from alpha beta to a, this part, the PDF becomes 0 again. So this integration, the integration for this part will always be 0. So that means like you add all those together, you say when beta is bigger than, sorry, when a is bigger than beta here, right? Your FA will be 1. Okay. So I think this is a very, very good practice for us to get familiarized about the relationship between PDF and CDF. So we encourage everyone to replicate these results by yourself after class, right? So here is just the figure showing the PDF of a uniform distribution and the CDF. So you see that before alpha, the CDF is always 0, right? And between alpha and beta, this is a linear curve, right? It's a linear function. But after beta, your CDF becomes constant again, which is simply 1. Any questions so far? Okay, great. So next, we're going to talk about exponential distribution. So exponential distribution are talking about a type of random variables which are always non-negative. So it means the value of the random variables are non-negative. So it is often used to model like waiting time between some events. Like say, you wait at the bus stop, you just use your watch to record the time interval between subsequent buses, right? And in practice, you often see those inter-arrival time of the buses follow some kind of exponential distribution. And similar, you can observe like waiting time when you are at a coffee shop, or you're waiting in Disney, you want to play some game, right? And those waiting time are often observed to follow some kind of exponential distribution. Another commonly used scenario to model is the lifetime of some parts, like a bulb, right? Like people often use exponential distribution to model lifetime of your bulb, like before a bulb, your light bulb is dead, right? How long it can last. The interesting thing is the exponential distribution lacks of memory. You might have heard this sentence, this weird sentence in other literature. What does it mean? It just means when you have a light bulb, right, and you use that for a while, and the good thing is it doesn't happen. It doesn't break. I mean, it is still working, right? And you pick it up and you clean it with your tissues, whatever, right? And then you install it again, and you switch it. You switch on. It's still lightning, right? It still give the light, and you want to ask, okay, given that it has already been surviving for 7 days, right? And what is the remaining life of this light bulb? The answer is that its life still follows the same exponential distribution. Statistically means that the life doesn't change. That is called no memory or lack of memory mechanism. So as long as it's working, that means your expected life will be the same. So it's a very interesting mathematical property of the exponential distribution, which can be derived through some like proof, but it's not the topic today, right? So we would like to introduce the PDF and the CDF for the exponential distribution. Okay? So what is the PDF for exponential distribution? It takes this form, right? So fx, I'm gonna use a color. The PDF function is parameterized by a parameter lambda, and it is lambda times e to the power lambda times x. And here we will require that lambda must be positive. Okay. So don't ask me why how this is derived. This is derived based on some like fundamental probability theory. It's not focus of our course, but we just want to give you this form. Right? So now, given this PDF, let us try to get its CDF. How do we derive the CDF? Any suggestion? No, infinity, right? To a, right? To some like input value of the CDF function, right? So we just leverage what we have discussed, right? So we know the CDF function at any input a should be an integration of the PDF from minus infinity to a and the PDF function times dx, right? So, but here we should be aware that we require that the exponential distribution is always non-negative. So meaning that our integration lower limit should be start from 0, not minus infinity. So that means we're gonna integrate from 0 to a f of x dx. Okay. So here is f of x, right? We just substitute it in, right? So it's from 0 to a, f of x has this form lambda e to the power of minus lambda x d of x, right? And to calculate this one, we need to recall our calculus 1 knowledge, right? So we just need to get the antiderivative function for this integration function, right? So what's the antiderivative of this? Yeah, yeah, you're right. But you need to don't forget a negative sign, right? So, I mean, if you feel uncomfortable or didn't catch up, doesn't matter. It's just need additional actual practice for this after the class, right? So the antiderivative will be minus lambda e to the minus alpha x. I'm gonna ignore the constant c because when you evaluate the upper and lower limit, they're gonna cancel out, right? So so why this antiderivative is just oh sorry, minus, right? If you just take a derivative of this guy with respect to x, guess what you can get, right? You take a derivative, you're gonna have a minus e to the minus alpha x and times minus alpha, right? I mean, take this guy over x, right? So you see that minus minus, you become a positive, right? So you cover the PDF, right? So this is just the practice of calculus, right? So now we get our antiderivative function, and then do this integration is simply to evaluate the antiderivative function value at the two ends, a and 0, and subtract and calculate the difference, right? Right, then this guy minus, you can remove minus by just switching the lower and upper limit, which is e to the minus alpha x and 0 and a, right? So if we just substitute 0 for x and substitute a for the x and calculate the difference, it will just give you 1 minus e to the minus alpha a. And therefore we obtain our CDF. Any question? Hope everyone feels comfortable with this. Okay, yeah. This is a good practice because on homework 3, you will need to either do an integration to get a CDF, or given the CDF, do the derivative to get the PDF. So it's better to make sure you're super comfortable with this. Yeah. Okay, here's just some figure showing the PDF under different choices of lambda. You see, we require the value of x. Here, x-axis represent the value of the random variable x, right? We require x always non-negative, right? You see, different lambda will influence the shape of the curve, right? This is a lambda equals to 2, right? This is a lambda equals to 1, and this is lambda equals to 0.25, right? 0.5. So basically, you can see the larger the lambda you see, the more steep decline from 0 to bigger values of x, right? And if we look at the CDF function, right, it will look like this, right? So this is remember CDF is 1 minus e to the minus lambda x, right? So you see different lambda will also will lead to different shapes of the CDF function. Basically, the larger the lambda you have, the more quickly the CDF will get close to 1, right? It will rise up. It will rise up more quickly. Right. Okay. Any question regarding the exponential distribution? Okay, great. So the next one we're gonna showcase is called a normal distribution, or the Gaussian distribution. This is perhaps the most widely used continuous distribution in statistics probability theory. You see that the Gaussian distribution or normal distribution actually is at the center of the probability theory. We'll talk about that when we when we talk about when we discuss about like the central limit theory law of large numbers. So so what is a Gaussian distribution? So first, it is for a continuous random variable, and these continuous random variables are in a full real space. Sorry, meaning that it is in minus infinity to infinity. It could be positive, could be negative. It's not like exponential distribution random variable, which can only be non-negative. The Gaussian random variable, a normal random variable, can be positive, can be negative. And this probability density function, right? Take this exponential to the minus quadratic form, and it is parameterized. It is parameterized by two parameters. One is called mu. The other is called sigma square. So mu and sigma squares represents or are also called the mean and the variance parameters. And as to like what does it mean for mean, what does it mean for variance, so we're gonna give the definition later. But here I would just keep in mind that okay, to determine a specific Gaussian distribution, you need two parameters. One is mu, one is sigma square. So this why do we use sigma square to indicate a parameter? Could anyone give a guess? Does it look like weird? Yeah, why it is so weird? Any guess? It's not a quiz, just to give me a random guess. No, normalizing. It just okay. So this is just be careful. Like this is like commonly used notation trick in the literature. So they use this guy. It's just to imply that this parameter must be a non-negative, right? Only non-negative number is can take as square of something, right? That's the reason. And that means like okay, if you want to determine or specify a particular Gaussian distribution, you got parameters mu, and then you have a non-negative parameter sigma square. And this sigma square does have meanings. We're gonna explain later, but here we just want to say okay, this represents the variance of the random variable. Okay. So the form of this Gaussian distribution looks like this, right? You see the main body is an exponential function, and then the power is minus, and then x subtracted by mu take a square, the over 2 sigma square. And the factor that multiplies with this exponential term is 1 over square root of 2 pi times sigma. Right? And the sigma here is also required to be a non-negative. Right? So this form sounds a little bit complex, but this is really, really fundamental. And you don't need to memorize every PDF function, right? But this one it's better to memorize that because you're gonna use them. Always use them everywhere, actually. So it's better to memorize this form, right? So given this PDF, how do we compute the CDF? Following the definition again, right? So the CDF is simply an integration of the PDF from minus infinity to a and fx e of x, right? So if I just substitute this exponential trajectory, exponential quadratic form into the integration. Right? Guess what's that, right? If you do an integration with exponential to minus a quadratic function of x, we from minus infinity to a, what does the result look like? Right? Unfortunately, there's no closed form for this. Right? You cannot write any closed form function to represent the result. This is a well-known result. So that means like you're going to memorize what's the form for that. And in practice, when we want to evaluate this CDF function, we have to use some numerical approximation method. Right? So this particular type of function is, if you look at the literature, is often defined as an error function. The error function just means like you want to do some integration over e to the power of x squared minus x squared, something like that. Right? So the computation technique for error function has been very, very mature, and they're like very fast and accurate libraries to approximate this CDF function. Okay, any questions so far about definition of the Gaussian distribution and its CDF, PDF? Okay, so then what does the PDF look like? Right? What does the Gaussian distribution look like? Right? You might have seen this type of figure before. Okay. So the PDF curve for Gaussian distribution is like a bell. Right? So sometimes you see people call this bell curve. It's a symmetric at the mean prime mu. Right? And the span of the span of this curve is determined by the variance parameter sigma squared. So remember, when we represent the Gaussian distribution, we say it is determined by your mean parameters mu and the variance parameter sigma squared. Right? So basically, the mean parameter mu determines where this bell curve stays, right? So here mu is 0, but when you move mu to be here, right, then you can see the bell curve will be moved to the right. Of course, mu could be on the left, right? And the bell curve will be look like this, right? It is symmetric at mu. And its span, right, or the width, right, very roughly speaking, the width is depending on the sigma square. So that means like the larger the sigma square, the wider of this curve, or you can view like the fatter the curve. Like so, when we increase sigma square, what you will see it will be like something like this, and if you keep increasing, it will be something like this. And when you take sigma square to infinity, what will it look like? Just give me a guess. Wild guess. Yeah, I would say it's a constant. It's like a uniform. It's like uniform distribution across the whole real space, right? The whole minus infinity to infinity domain. And you can show this if you take the sigma squared to infinity for this form, you will see it becomes a constant. Right? It's not necessary to be 0. It's not necessary to be 0. Okay. So if you look at the CDF, which doesn't have any closed form, it will look like this. So as we mentioned, right, CDF is like when we say, if I want to look at the CDF value at A here, right? So it basically means, okay, the area covered by the PDF from -infinity up to A, right? So that means like if you increase A, the area covered by this PDF curve will become larger and larger, right? Right? Remember, the definition of CDF is integration, right? Right? It just means like, okay, up to A, how much area does your PDF curve covers, right? So increase the A, you're gonna enlarge the coverage. That means you got a larger and larger area to cover, right? And of course, when A goes to infinity, this becomes -infinity to infinity fx dx, which is 1, right? The whole area covered by our PDF is 1. So that's why we see the CDF is always kind of like a monotonically increasing, right? Because when you increase A, you're gonna have a larger and a larger area covered by the PDF curve, and eventually your total area will become 1. That's why you see the CDF curve is converging to 1. Any questions so far? Yeah. So one thing I want to disclose prior to our discussion about central limit theory is why Gaussian distribution is so important. You see that later we'll discuss about details, but here I just want to give you some sense. Like, if I have some random variable like x1, x2, xn, right? So imagine you're doing n independent trials of any experiment of interest. It's not necessary to be Bernoulli experiments. It could be any distribution, right? And including the Bernoulli experiments. Remember, the Bernoulli experiments, each of your x1, x2 are either 1 or 0, right? And if it is an exponential distribution, it could be a positive number. If it is a Gaussian distribution, it could be either positive or negative number, right? So the interesting thing is that when you take an average of those random variables, those independent, identically distributed random variables, when you increase n, meaning that you're doing more and more experiments, then the average of those all n random variables values, which is another random variable, its distribution will look like more and more to a Gaussian. That's kind of amazing stuff, right? So no matter what kind of like a distribution those x1, x2 through xn follow, right? No matter x1, x2, xn are discrete or continuous, if you repeatedly doing the same experiments independently and take an average of all those variable values, those average will behave more and more like a Gaussian distribution. This is called central limit theory. That's why Gaussian distribution is so important. Okay, we're going to discuss about this later, right? But just to give you a sense, like why Gaussian distribution is useful and widely used. Okay, so the last continuous random variable we want to introduce is called Pareto distribution, right? This Pareto distribution is still is for the positive numbers, and here we require that the random variable x must be no less than 1. Right? The PDF of the Pareto distribution looks like this. It is parameterized by some parameters alpha. Alpha must be positive, right? Alpha over x to the power of 1 plus alpha. Right? For example, if you take alpha equals to 1, the density function will be 1 over x squared. Okay. If alpha takes 2, your PDF will be x over 2 over x to 3. Right? That look a little bit weird, right? So the denominator, you got a polynomial, right? And in the numerator, it's just a constant. Right? So what does this distribution represent? Right? The Pareto distribution is often used to model those highly imbalanced distribution, or it is used to model unfairness. I mean, we want our society, want our world to be fair, right? And to be balanced. Unfortunately, this is not true, right? And it will be unfair forever and ever, right? So you might have heard those laws like you no matter in what kind of society, right? Even in communism society, you will say 20% of people will own like 80% of wealth, right? And 80% of people will only share the remaining 20% of wealth. You see this kind of phenomenon everywhere, no matter in what kind of social system, right? And in market, right? Even in free market, you see like, okay, in any particular market, right? You see a few big enterprises dominant market, right? It's not like, okay, this whole market 10% share belongs to this company, and the other 10% share belongs to the other company, and so on. It's not even a distributed. Instead, like the majority market share are dominated by just a few companies. Right? If you're from CS, you know that, okay, looks like the whole internet market are dominated by just a few companies. Everyone knows that, right? Apple, Meta, Microsoft, Google, and so on, right? And then for the remaining very little market share, they're occupied by maybe 10,000 companies, which you never have heard of. So the Pareto distribution is often used to model this kind of phenomenon, and also associated with so-called power law. Right? So here are just a few examples, like models wealth distribution, file sizes in the internet. The richest few own a disproportional rate amount of total wealth. A few big corporations dominate the market. A small number of files in the internet are huge, while most are small, and so on. So here we want to show how we arrive at the CDF function from the PDF. Again, this is just a practice. So the CDF, according to the sorry, it's 4:30. Okay, let's just take a rest for 5 minutes and then continue. Hey.
On the slides, it shows this is the equation for Gaussian distribution, but on the line it shows
It's the same.
it's the same thing. They don't.
Yeah, if you take the sigma squared and take the square root, it becomes sigma.
Yes.
Yeah, it's the same.
Okay, gotcha.
Yeah,
Yeah. You just decided to pull it out.
yeah, yes.
Okay,
Yes,
that's good.
Okay. Hello, everyone. Let's just continue, right? So here we want to make a additional practice about calculating the CDF function. We keep doing this because we want to strengthen your understanding about the relationship between PDF and CDF, right? So the CDF is an integration of the PDF function from minus infinity to a, and the integration function is the PDF function, right? So here because the Pareto distribution requires that the random variable value must be less than 1, right? So the lower limit of this integration should be from 1, right? 1 to a, and f of x here we just substitute the actual form into the integration, right? And d of x, right? So I can write it again here. 1 to a alpha x to the power of alpha plus 1 d of x, right? So again, anyone can point out what's the antiderivative function for the PDF, meaning this guy? Right, that's just make us record what's the antiderivative function for power function, right? So we know that if you take x to the power of say beta, right? So you know the derivative of this guy over x is beta times x beta minus 1, right? Right, that's the rule, right? So if you look at here, it is better to write it as alpha and x minus alpha plus 1, right? It's just another way to write 1 over something, right? You just take minus sign in front of the power, right? So that means we got minus alpha minus 1, right? So the antiderivative following what I'm saying here is just x minus alpha and negative sign, right? You can check it by taking the derivative of this guy. You will see that it is exactly the PDF here, right? So that means the integration is simply evaluating the antiderivative function at the two ends and do the difference, right? That gives us 1 minus a to the minus alpha, right? Which is here. Okay. Any question? Okay, so here is just a showcase the curve of the Pareto distribution. And how does this curve vary along with different choices of alpha? And this is a CDF function, right? And again, the CDF function is always monotonically increasing, Why? Because the CDF represents the area covered by the PDF curve, right? When you increase A, right? When you increase the input to the CDF functions, you're increasing the area covered by the PDF curve. So of course, you increase A, you're gonna increase the area, you're gonna increase the CDF function. That's why the CDF function is always monotonically increasing. Okay. So then we'd like to introduce the concept called quantiles. What does quantile mean, right? So quantiles specify a particular type of location at which your CDF function is the given specific probability. Say, I want to know at which position my CDF value is P. Right? Say P could be 0.5. I want to know which value of X can give the CDF function value as 0.5. Then this value is called the quantile, the 0.5 quantile. In other words, you can view it as kind of an inverse of the CDF function, right? I know, I want to know, okay, when the CDF is 0.5, right? What's the corresponding input to the CDF? Here it might be 1.9, right? So then I call 1.9 is the 0.5 quantile of this distribution. Does it make sense? Right? And when I was a student, I was very easily confused by this concept, right? So what does quantile mean? Quantile is just a way to to say, okay, I want to say inverse mapping of the CDF, right? If we use Gaussian distribution as an example, that might be even more clear, right? Oops. So if I take my P equals to 0.5, meaning that I want to know at which input location that make my CDF value to be 0.5. From this figure, can anyone tell me what's the 0.5 quantile? Yeah, just 0, right? So if you take a look on the y-axis, you see when your value, when your P equals to 0.5, the corresponding X value for the CDF is 0, right? So the quantile 0.5 quantile for a Gaussian distribution is simply 0. Right? Of course, people might not just interested in 0.5 quantile, right? They might ask, okay, what is the quantile for P equals to 0.95? Well, you don't need to tell exact number because I can't memorize that as well, right? But here, what we need to do is that, okay, I'm gonna pick up the point at y-axis, right, which is 0.95. I'm gonna draw a horizontal line to cross the CDF function, right? And then you look at the cross point, what is the input, right? What is X? That is the 0.95 quantile. And by the way, what I draw here is wrong. The 0.95 quantile is bigger than 2. I just some bad drawing, right? So in the old, old times, like maybe in 90s and 80s, like people don't have like computers to do that. They have some book, they have some dictionary. I say for Gaussian distribution, what is the 0.95 quantile? What is 0.5 quantile? What is 0.05 quantile? What is 0.99 quantile? They have already computed that and then placed them in the dictionary. You just read it. Okay. And in particular, like 0.5 quantile, sometimes it's called 50th quantile. I mean, if you want to count everything in percent, right? 50th quantile is the same as 0.5 quantile. This quantile is called median. That's the rigorous definition of median. Meaning under the distribution, right? And at which position you're gonna have the CDF value to be 0.5. So that basically means, okay, my probability of your function, your random variable value less than or equal to this quantile is half, right? Or the bigger than this quantile is half. It's the same thing, right? That's called median. Right? Want to know, okay, at which particular position, such that if you split the values around the variable into two halves, right? And the left halves will take 0.5 and the right halves will take 0.5. This is all very, very often used in social analysis, economic analysis. Like, for example, maybe you have heard often, like, what is the median income of this whole country? It's much better. It's a much more objective evaluation of the development of the society than you just take the average, right? If you take the average, imagine like you got very few people owns like 99% of wealth in the nation, and then you take the average, looks like everyone everyone gets the everyone is rich, right? Actually, it's not like that, right? That's why people always look at median, right? If the median is good, that means like most people are good, right? Okay, any questions so far? Okay, so and given the definition of the discrete random variables and continuous random variables, and also their associated PDF and CDF functions, we'll then introduce two very important concepts, which kind of summarize the properties of those distributions, which are called expectation and variance. Right. So let's start with oops. Let me just put this. So let's start with the definition of expectation. So what does expectation mean, right? From intuition perspective, it just means an average, right? Because we have some random variable x, right? And you know that x can take a variety of different values, which reflect how the samples and outcomes in the sample space map to those values, right? Of course, they're gonna have some varying chance to take different values. Then people would like to ask, okay, intuitively, on average, what value does a random variable take? Right? And how do we define that, right? For discrete random variable, it is just defined as the weighted average of the value the variable can take, right? So suppose you can take a set of values like A1, A2, A3 to say A10, right? So you know that associated with each value, you're gonna have some probability your x takes this value, right? Now, to calculate the average, to calculate the expectation for this random variable, I'm gonna just take the weighted average of all the value it can take. And the weight is simply the probability the random variable takes each value. That's it. And how to understand this, right? So you can imagine that you're doing some kind of random experiment. And when you throw a die, or when you throw a dice, or when you do some gambling, right? Every time you will see some outcome. And just keep doing this, keep doing this, keep doing this. And on average, what's the value you observe? Like, for example, you just flip the you just flip the coin, right? In first experiment, you see 1, second you see 0, third you see 1, fourth you see 1, 0, 1, and so on, right? And then you just take the average of all those values. You want to say, okay, on average, what's the value you can see? If the value is bigger than 0.5, see the average value is 0.8, that means, okay, looks like in most cases, you will say the heads up, right? If the value is 0.2, for example, you might say, okay, in most cases, you will say tails up, right? So a more rigorous calculation would be I just do a weighted average on every possible value the random variable can take. And the weight is simply the probability your random variable value takes this value. Okay, any questions so far? So now we start with the first example, the Bernoulli experiment, the flipping the coin example, right? So suppose our random variable x follows the Bernoulli distribution with parameter p. Remember, p represents the chance you succeed, right? The chance you see 1, right? So that basically means the probability x takes 1 is p. The probability x takes 0 is 1 minus p, right? Then the expectation of x, as we mentioned, is just a weighted average of the value x can take, of the values x can take. We can take two values, 1 and 0, right? For x takes 1, the weight is the probability x takes 1, which is p, right? And for x equals to 0, right, the weight is the probability x takes 0, which is 1 minus p. And what's the result? What's the result of this guy? It's just p, right? Yeah, that's a very well-known result for Bernoulli distribution. The expectation of a Bernoulli distribution is simply p, the parameter that determines this distribution. Does it make sense? Everyone's comfortable about the calculation, right? Just be aware, this is used everywhere. Like actually, the expectation of Bernoulli random variable is just the probability that random variable takes value 1. Remember p here, it just means the probability x takes 1. Okay. Another example is geometric expectation. So can anyone tell what's the geometric distribution? Anyone recall? Yes, exactly, right? So it's different from binomial experiment where you just want to look at how many times you guys succeed, right? So the geometry distribution just means like at which trial you will have your first success. Meaning that if x takes 3, that means the first 2 trials all fail, and you succeed at the third trial. And x equals to 10 means the first 9 trials fail, and you succeed at 10th trial. So obviously, if x follow a geometric distribution, the value of x can take to be 1, 2, 3, 4 until infinity, right? Does it make sense, right? You might fail until you try the 1 millionth time, right? Or 1 billionth time, right? And theoretically, k can be as large as possible, right? As long as k is just a positive integer, right? And we know that the probability mass function x equals to k, meaning that you're gonna fail in the first k minus 1 trials and succeed in the case trial. So this probability is 1 minus p to k minus 1, then times p. Does it make sense? Right? So that means if you want to calculate the expectation of x, the definition, right? We have to do the weighted summation for every possible value x can take, right? So it could be, x could be 1, right? 1 times p, x equals to 1, 2 times p, x equals to 2, right? So if you write it in a more compact way, it is just a summation. Now all possible values of k, those k can choose from 1 to infinity. And then you multiply k with p of x equals to k, right? Right? And p of x equals to a is here. So I'm just copy the formula here. Is p times 1 minus p to the power of k minus 1. Right? You see this is a series, right? It's a summation of infinite sequence, right? And the good thing is that this series converge, meaning that the expectation exists, and the result is 1 over p. Right, as to how we derive this, it will need a little bit trick. It's not very obvious here. Remember, this guy is not a geometric sequence, meaning that if you just look at a fraction, you just look at ratio from successive terms, so they are not constant. So yeah, you have to leverage some kind of trick to solve that, and let's solve it in the next lecture. Okay, see you on next lecture. By the way, we're gonna have the class canceled on next week, and perhaps we'll see you the week after next week.